Hello, everyone. My name is Peter Darrington. I'm the Chief Strategy Officer at Answeralytics, but more importantly, I'm delighted to be the session host for this session with Kuba. And we're going to be talking about developing intuition for AI as a leader and the path to data literacy. So, briefest of introductions for Kuba. He's an experienced software architect and a CTO, passionate about helping people and companies work more efficiently with artificially intelligent software. I'm sure he's going to tell us a little bit more about that in a moment. But developing an intuition for AI is a critical role for the modern leader, and it strongly correlates with success in today's business world. So during this presentation, he's going to be giving us a seed of what this intuition looks like and exhibited by going a little bit deeper than most executive guides to AI. So without any further ado, I'm going to hand over to Kuba. I'm going to disappear off stage so that I can watch this myself. But Kuba, over to you.
Right. Thank you, Peter. And hi, everyone. So my name is Kuba Misiorny, and like Peter mentioned, I would like to explore with you today what artificial intelligence really is and how to effectively drive innovation in your companies by having this intuitive understanding of it. So in my company, Untried, we're building an AI-powered augmented intelligence platform, but we as well help organizations add to their bottom line by analyzing their business processes and designing bespoke intelligent data solutions that augment their employees' work. So this cartoon illustrates everything I want to convey in this presentation. So when a manager or a project leader comes in and says, when a user takes a photo, they have to check whether they're in a national park. The engineer says, sure, I'll need a couple of hours and a simple geographical lookup. But then the manager says, and check whether the photos of a bird. And the engineer replies, we'll need 5 years and $10 million to achieve this. And I think for us engineers, this might be obvious that one thing is very easy and one thing is very difficult. But for people, non-technical people that are looking from the outside at all this technology, some of those things are very unintuitive, and they don't understand why one thing is very easy and one thing is very difficult. And I think having the intuition for the technology that builds the products that we are making and we are selling helps in those discussions and helps communicating between the technical and the business world. But so actually imagine a business without computers. I used to do a little bit of trading in the 90s. I had to do my research about stocks in a library and newspapers. I would phone in my broker and ask them to put in a bid for me. I imagine them like scribbling my order on a piece of paper, then maybe transferring it into an old computer, maybe some spreadsheets, some early spreadsheets, and then sending that order to an exchange. So I asked myself a question like, would a business like this, like mine, trading stocks, would that survive in today's world doing research on this outdated information in the library? And of course it wouldn't. And so leaders that embraced computers in those early days and surround themselves with people that see the potential transform their organizations. Of course, the flip side of that is that companies that didn't do that are not with us anymore. We don't even remember them. It's even difficult to imagine a business that's not using computers in some shape or form today. And I think artificial intelligence is at least as important of a technology as computers are. Of course, AI builds on top of computer technology. We are all standing on the shoulders of giants. But make no mistake, this is not an incremental change. This is not a 10% better than before. AI represents a dramatic shift, a revolution, if you will, of how our technology can process, perceive, and interact with our world. So in our experience at Untried, a lot of executives get this, but then jump on this AI train a little bit too fast. I've been in many conversations when someone said, like, we want all of the AIs. But the motivation sometimes it's not really great. People want to build AI or get involved in an AI project just to be able to say that they are using AI. And then a lot of them don't fully appreciate the complexity of those endeavors and are really bound to spend their budgets without a lot to show for it. And so we're there to help. We're there to analyze the processes and propose concrete AI solutions that actually solve real problems. But I sympathize with those leaders. I think it's very difficult to lead a modern organization without an intuition for the technology that builds it. And so developing such intuition is this critical role of a leader, and one that I think that strongly correlates with the company's success. So this presentation is a version of the presentation I or some of my people give to our clients, the leaders that we work with, that builds this intuition. So of course, this is just a 45-minute presentation. I can only give you a seed of this intuition, but I'll try to do this by going a little bit deeper than most of those executive guides to AI that you can read online. So in my view, the best way to assess an impact of technology and technological change is through a business perspective, and to ask fundamental questions. And there's only two questions: either how does the technology reduce cost, or how it can produce value. After all artificial intelligence deployments, actually any technological deployments, should be a response to a business strategy and not technology trends. And so let's dig deeper into this analogy between AI and computers. So I'm a big fan of thinking from first principles. And so if we boil down computers, we arrive at one thing. Computers are really one thing. And that thing is arithmetic. The magic of self-driving cars, high-frequency trading, high-speed internet, all of this is built on computing numbers. Deep down, computers are just souped-up calculators. The fact that they appear to do more is a testament to the power of arithmetic. It's like this, the Conway's game of life. There's a very simple simulation of kind of one-bit automaton. There's like very simple rules, but a lot of complexity emerges out of the simple rules. So the same thing happens here. Arithmetic is a simple, has simple operations in it, but when they're put together in a certain way, a lot of amazing complexity emerges. But so let's frame that through those two business questions, the computer revolution. So this semiconductors reduced the cost of computation, freeing up the original computers, so people that actually calculated numbers. I am sure you've seen scenes in movies where there's like rows of people just banging on kind of specialized typewriters. Those were just calculators, and they calculate strings of numbers. So this cost reduction happened at the beginning, and later that led to the production of value in thousands of new applications for everything from data storage to word processing. And that's a very important aspect in how a lot of technological change happens. The value production happened later after the initial cost reduction. So usually what happens is you have a process that then a new technology can optimize, reducing costs, but then that new technology has some aspects to it that then gives place for new technology and new business sectors to emerge from. And so the intuition here is that the link between computers and arithmetic was very clear in the early days. Today, we don't even remember that link. Today, only very, very specialized people remember that link and work on improving the arithmetic in the computers on a very low level of the whole computing stack. And so I think the same thing is going to happen with AI. Today, AI is used by very specialized people that know it intimately. And today, AI is mainly reducing costs and optimizing processes. We're already starting to see the effects of the direct value production, for example, in the generative AI space. I'll be talking about that later on with some other brilliant colleagues on a panel discussion. I think at 1:30 today, 1:40 today. And so, but soon AI will be creating whole new business sectors, and it's going to be so ingrained in our society and business. It will be really unthinkable for a company not to use AI in some shape or form. So the task that AI makes abundant and inexpensive is prediction. And I'll show you how advances in AI are linked to that and how that relates to the value of some human skills and what are the implications of the changing of the human skills for the business strategy and for the leaders as a whole. But let's define AI first. So this term, artificial intelligence, it's very loaded. It has been stretched and reformed for marketing purposes, losing its original technical and useful meaning. It's a very broad term that ranges from concrete, deployable solutions to science fiction fantasies. So from that picture, I'm clearly talking about AI down in the bottom right. But I love application of technology that provide clear value, where we can have very well-defined KPIs where we can measure the success of the project against. So I want to take all of this down a notch and talk business, not buzzwords. So for the rest of the presentation, when I say AI, I mean something what's called narrow AI. It's an application of AI technology to a very specific and very clearly defined problem, like playing Go or detecting fraud in bank transactions. It's in a contrast to something called general AI, which is a system that can solve many problems on its own, and a system that's essentially self-aware. Nothing like that exists yet. This is a stuff out of science fiction. It's the Matrix or the Skynet from the Terminator. And talking about this is more of a philosophical discussion, and this is better taken up over a beer later on in the evening, which incidentally is something I was really looking forward to doing with all of you, but unfortunately the conference is virtual. So, of course, the line between narrow and general AI is moving, and to the point where there's this joke in the community that AI is all cool things that computers cannot do yet. So some of the projects and things that we'll be talking about later on, they were not possible 5 years ago. And they were glorified as this artificial intelligence, meaning the general artificial intelligence. But now those algorithms are barely machine learning, which is sometimes this dirty word in the community. So machine learning is the specific applicable part of AI. All the implementations you hear about are exactly that, machine learning. And the ideas behind ML are simple. And we will be able to go through some of them today to develop this intuition I'm aiming for. And hopefully that intuition will help you lead your organizations. So the broad idea behind machine learning is that there are generic algorithms that can be applied to many problems without writing any custom code. So the thing that changes between those applications is the data that you feed those algorithms. So let's see how that works. So this is the part where we'll get a little bit into the weeds, and we'll build a rudimentary machine learning model. So this is the keyword. In machine learning, you build models of the real world that, model the real world. So let's say you're a mortgage agent. Your business is growing, so you hire a bunch of new trainee agents to help you out. And so while you can glance at the house and have a very good idea of what it's worth, your trainees don't have that experience. So to help them, we'll build a little machine learning model that can estimate the value of the house. So we can estimate the price based on the number of bedrooms, the size of the house, and the neighborhood that it's in. So the circles that we see on the slide are called neurons. So a machine learning model is comprised of neurons. But bear with me, this is just a fancy word. Those are, underneath those are really just mathematical functions. So they take number of inputs. So they take numbers as inputs and perform an operation on those numbers and then output another number. So for example, they might multiply or divide a number on their input by some weight, which is just another number again, and then output that on the output. So there's something missing here, the connection between the input and the output. And again, those circles are more of those mathematical functions that add or subtract numbers or multiply them. So this is really our machine learning model. This is it. This is our algorithm. A bunch of mathematical functions connected together in some very specific way. And so the neurons in the middle of our screen here are called a hidden layer. So for the sake of, wait, I think I have a. Right. So the neurons in the middle are called a hidden layer. And so for the sake of simplicity, I only drew one here, but there can be many layers. And usually there are many layers with many neurons in those layers. And it's called a hidden layer because traditionally machine learning models were really black boxes. So you just see the inputs, you just see the output, and there's a box in the middle. Something happens inside, you don't know what's happening. Right now, there is a move to actually explain some of the things that are going on inside the models, but we'll touch upon this later. All right. So for this to work now, we need to train our network, and we do this by showing the network some historical data. So this training is the learning in machine learning. So one of our training data would look like this. We have an apartment in Islington that has 200 square meters big, and has 3 bedrooms, and it's sold for. Sorry, I made this slide a couple of years ago. I think I need to add one more zero here probably now. But I digress. So this is our training data, and so now is where the magic happens. So we plug in those numbers into the model. And at the beginning, the answer will be random because the network was initialized with random numbers. So each of those hidden layer neurons would have some number in. For example, it will take all of the inputs and multiply them by 10, and then this neuron will divide everything by 20, and so on. Right. So those numbers are random, essentially random at the beginning, and so. Now we compare the actual real world value, so the 1 million that we had in our training data, with the predicted value. And through that, we teach the network how wrong it was. The network will adjust the internal calculations to be closer to that intended value. So of course, we repeat this training process many times with much more training data, so that the network can properly model the real world. It's sort of like a human learns, right? You need to see a lot of examples of something to be able to learn it and build this representation of that phenomenon in your head. Of course, the way the network adjusts the weights and calculations they do internally is very well defined, is very precise and studied. But I omit all of this here for clarity. We're not going for a data science class here. The specifics are not really needed for this intuition I'm aiming at. You just need to know that machine learning models model the real world by comparing the results of the training data, by comparing the results that they get with the training data, so that they can adjust accordingly. And another thing to note here is that, as I mentioned, that was really a total example. A real world ML setups are a lot more complicated. They might have hundreds or even thousands of layers with hundreds and thousands of neurons in the hidden layers. But the magic here is that the same network will learn how to predict a stock price or identifying which job candidates will be the most successful. And another incredible thing here is that the AI model can find features in the data that we couldn't have predicted as humans. but it can go both ways, right? So in our example, maybe there is some strange correlation in the data that indicates that the houses with square footage that's divisible by 3 are 50% more expensive. And possibly this is something that's an actual phenomenon in the real world. So if your machine learning model finds a pattern like that, that's true in the real world, you can capitalize on that and make your profits higher, right? But of course, the inverse of that is true as well, right? If your training data is not great and has some quirks like that, machine learning model might find that, and then you have a model that's not really close to the real world. So there is a whole world of explainable AI that seeks to understand the outputs of machine learning models and help us understand why some predictions are the way they are, and through that we can reason if it's might be true or not. That way we can as well do some analysis on the training data and find patterns that are, for example, bad for us. I'll talk about that a little bit later on in more detail. So again, the very important part of the intuition here is that the difference between a good and a bad machine learning program is that it's not how smart the algorithm is, or at least not in its entirety. It's the quality and the quantity of the data that you feed it. So that's why Google and Facebook need your data so badly to stay competitive and to make better predictions. So I think this toy example that we looked at is a first great step towards the intuition for machine learning. It explains why we need good training data. So the better the data and the closer it is to the real world, the closer the model will be to predicting real world values. But this also speaks to the bias of machine learning. AI or machine learning are not inherently biased, and the results they produce might be biased, but it is based on the data that you feed it, because that's the only way machine learning models learn about the world, through the data that you show it. And that's how it's going to adjust the weights in those hidden layers based on the data. There's nothing else. So if you're surprised that an AI model that ranks CVs for technical position, that it discriminates against women, this is not an internal bias of the engineers that build that model. Guess what? It's the years of historical data that show that bias. If an organization hired 90% male engineers in the past, and you feed that data into machine learning model, this is what the model will output. That's why we need to take great care when building, training, and operating those systems. And actually, the exercise of building a machine learning model, for example, for this CV application, can help us identify those hidden biases that no one saw before. And this is exactly down to the explainable AI paradigms, right? So when we're training a machine learning model and we see that certain names get disproportionately better results, better outcomes of that model, maybe we see that there is some discrimination in our historical data, and we can correct both the organization, so like the organization layer of our hierarchy, but as well we can filter this data or change it so that it doesn't exhibit this kind of bias. But speaking of bias, this word again is being used in marketing purposes in a way that it's kind of been reformed and means this bad thing, right? We actually do want bias in machine learning models, but we want the good kind of bias, right? We want the models that are biased, are discriminate towards correct answers. So we want them to be biased in this correct dimensions, whatever those dimensions are, right? For example, in the CV example, we want the model to be biased towards people that are qualified for the role. If the model wasn't biased towards good candidates, its answer would always be maybe, or essentially a coin toss. Coin toss is not biased, but it's also not very useful. So bias can be a good thing. Well, it is a good thing if it is towards good dimensions. And so if we want to use AI for the benefit of our organizations and understand those concepts, we need to develop a data literacy culture. And so how do we do that? Data has been called new oil, but I think we need to step back from this statement to understand it a little bit better. So data is this valuable asset. There is no question about it. But just like oil, it has to go through people and refinement to get value out of it. So data literacy is understanding this and then having tools to do it. So according to Gartner, poor data literacy is one of the main roadblocks to the chief data officer's success and companies and certain companies' ability to grow. So fostering data literacy gives people this mindset to think and communicate using data. And this should be the data that you already have in your company. So through that culture, people naturally find opportunities hidden in the data and can begin to verify those. Of course, I'm not saying everyone should be a data expert. So further down the line, it's good to surround your company with experts that will help you realize and benefit from those different opportunities. So circling back to our fundamental business questions, machine learning reduces cost of prediction. And while being able to do it more accurately and much faster than what humans can do. And even further, the more and the better data you provide, the better it will become. And so more complex tasks it will be able to model. So in this context, let me ask you this. What percentage of your employees' work involves prediction? All of those jobs could be augmented with AI. And I really mean augmented, not replaced. So in our work, we always start with kind of the most mundane tasks, and happily those are the ones that the machine learning is usually the best at, and the people, and those are the ones that people dislike the most. So automating those small tasks frees up capacity, leaving people to do things that are uniquely human. So expressing their creativity and their human judgment. So to the point where I believe that the most valuable workforce skill in the future, it's already starting to be like that, but in the future even more so, most valuable skill will be judgment. So in many work activities, this prediction has been this bottleneck to automation. In some, such as reading, handwriting, documents, or in general understanding human language. The bottleneck has meant that human workers have remained involved in those kind of small piecemeal prediction tasks. So here the definition of prediction is very broad, as is the arithmetic definition in what computers are doing. So prediction can be, for example, predicting if a PDF document will be a suitable data source to solve a problem of a customer in a customer support setting. So how can we redefine those tasks? How can we redefine more and more tasks as prediction tasks that are suitable for AI? How we can expand the reach of AI and help it understand our world a little bit better. So let's zoom out a little bit and think about robots. Why is Boston Dynamics and other companies, notably Tesla recently, why are they developing humanoid robots? It's very difficult to make a robot that walks on two legs and operates humanoid hands, right? Like the Atlas robot that we see on the screen, Boston Dynamics Atlas. It took them years, over a decade, or even more, to build a robot that can balance on two legs and walk and do backflips and all sorts of things, right? It's much easier to build a robotic train, for example, than to build a self-driving car. Or even easier, build a robot that doesn't move, like in factories, where the materials come to it in a structured and predictable way. And of course, we know the answer to that. It's obvious. So while an alternative to self-driving car is a robotic train, we have a lot of those. But the challenge here is that you need to build all the infrastructure around to support them, right? So in this example, you have to build train tracks, and you can't really build train tracks to every house. We already have infrastructure for that, and it's called roads. So there's a limit of how much of the world we can structure in a way that's suitable for suitable and accessible for those kind of different robots. It's clear that most of the world is already designed for humans, and to be able to access that world, at some point you need to emulate humans in one way or another. And so this exact same scenario applies to the knowledge work. Looking at unstructured data, for example, looking at unstructured data in the form of text. Most of that text is made by humans and for the humans, right? All the contracts that we write, emails, instant messages, notes, are all made for other humans, not for computers to understand. Even code, sure, it has to be understood by the computer, but it's actually made for humans. There's this ancient wisdom in software engineering that you're writing code for the next programmer that will be reading it, even though that the next programmer might be you. And so to be able to access that world of knowledge and information and interact with it, you need computers that think like humans and understand human language. And in all of its messiness and lack of rigid structure, right? So imagine you have 5,000 legal contracts and those are scanned paper documents. How do you find all the contracts that provide a certain rebate structure or certain warranty? This is not something that you can solve with keyword searches and some rigid regular expressions or structure rules. Even if it worked for those 5,000 contracts, you add one more contract and everything can break. So traditionally, you would farm it out to human intelligence operators, namely interns or graduates. But this is where the new wave of NLP, so natural language processing, so this type of machine learning models that aim to understand language, this is where those new models shine. As with humanoid robots, NLP allows us to interface with this human world and do things that humans couldn't do or would take them too much time. So imagine instead of 5,000 contracts, we have 500,000 contracts. It would take weeks and weeks of even the biggest, the smartest group of interns. And so this is where the deep learning comes in. It allows computers to begin to understand the unaltered, unprepared human world. So deep learning is really built on those machine learning models that we talked about before. They're just deeper. There's more layers in those models, and they're arranged in a certain way. But so what, you ask, right? Humans understand human world, but computers can bring unique benefits. So like I mentioned before, they can attain this perfect visibility of huge quantities of data. But making decisions and making judgment based on that data is a whole another story. And for mission critical applications, you want to have this human judgment somewhere in that process, mixed into this decision model. So this kind of approach is called human in the loop. But I'm a big fan of a different term that has a bit more zing, augmented intelligence. So let me show you one high-level real-world example of that, and I'll wrap up. So say you're an engineer supporting a client that has a problem with a machine that you sold them, right? So what kind of information will you need to efficiently and effectively help your customer? You'll need this client information, you need some history of the issues this client has raised, maybe a list of machines that you sold them, a history of the issues with that machine, and the ways to debug it, and the ways to fix it, right? And all of those files, all this information lives in a different system. You have customer support system, accounting, CRMs, ERPs, a big chaos of a lot of information. And so for a human operator, it will take a lot of time and a lot of thinking, like, all right, I have to go to this system, that system, and then actually search through those systems to find that information. Wouldn't it be great if the context of that request, containing all of the information from all of those different places, was presented to us based on each request, right? So that we as humans can focus on understanding the problem, understanding the context of that problem, and then providing a solution to the client. So this is the interesting part of the situation, right? Figuring out the solution, connecting the facts, and applying this judgment and creativity. The interesting part is not looking up all of this information in all those different various systems. So how can we achieve this? So again, deep learning, NLP, so natural language processing system is the answer here. NLP models can understand language, and more precisely, it can understand the meaning behind the words, sentences, paragraphs, or even whole documents. And through that understanding, we can automatically build this ephemeral map that connects all the different systems, all the different documents throughout the organization that relates to this specific issue that we have at hand. So based on the description, right, for example, fuel engine reporting faulty, we can find the error state that this machine can be in on some intranet page in our organization. And we can read that error state page and find out that it prescribes some actions of how to fix that problem, right? And based on that, we can find a SharePoint PDF manual that talks about the procedure for replacing the speed sensor. We can go even further. We can understand, the NLP can understand, all right, XYT46 is this model number of that speed sensor, and take us directly to the spare part Excel spreadsheet that we have that contains an order number, which will take us directly to an ERP system where we can order this spare part. And so imagine being presented with this immediately after the user types in that fuel engine reporting is being faulty. You don't have to think about all of this. You don't have to follow all of those steps. The AI presents all this information to you, and you shine there with the human judgment and human intuition of how to fix the problem based on all this information. And so here's a live product that actually follows that logic, where based on, say, a Jira ticket, we present the whole context of that context created from the organizational information based on that ticket. So to wrap up, there's no question, AI is changing the business landscape and this internal work balance. And to be successful in this new world, leaders have to embrace this new technology. And I think the best way is through intuitively understanding it, fostering this data literacy culture in the organization, and then actually cultivating this uniquely human judgment-based skills in your employees. So the ideal, happiest combination is this advanced technology that takes care of these mundane, boring tasks. So a prediction-focused AI, and people that can use it to augment their problem solving and creativity. Thank you very much. I think there are some questions.
There are indeed, Kuba. Thank you very much, firstly, for a great presentation. Really enjoyed it. I've got loads of questions myself, but we have had the question come in. It referred to your earlier example. So let me just read this out. So how would you deal with trend effects in an artificial neural network? In the example, predicting current prices from static variables like area, district, and the number of bedrooms from historical data, how would the accuracy of the prediction look in the context of, well, it says out of time data here, but I would actually say changing data. And I suspect part of the thing that I was thinking of is, how do these models deal with volatility? So when we've got big shifts going on in trends. So I'd love to hear your thoughts about that. How do we deal with those non-static variables?
Yeah, this is a whole another topic for a long long presentation as well, right? Of course, in those traditional kind of first models that dealt with that, they just didn't, right? They could just look at the static data that they had, and this is the whole that was the whole worldview that they had, right? They didn't have a concept of that volatility. or maybe they did, right? If there was some volatility in the historical data, they could maybe understand different patterns that causes volatility and be able to predict that. I think someone, when they are talking about out of time data, what I understand, they mean that there is like in my example, right? This flat in Islington, it's not going to cost £1 million. It's going to cost 5 now, because the data that I had was from 5 years ago. And so this is actually called a data drift, where if your models stay the same, they will just get stale. This is the same thing as a human would do, right? If you had a real estate agent that worked in the field 5 years ago, they would have this model, and then they went to the woods and stayed there for 5 years and came back. They would have this outdated model, right? They have to see new data. And so that's how machine learning models are used today as well, right? You have to have a continuous, maybe even a drip of data that will retrain those models. And so there's different techniques of dealing with, so say you have like a big amount of data at the beginning to train the model, and then only have little bits of data. You kind of give this new, fresher data, basically kind of a bigger weight, right? That this fresher data counts more in the model than the older data, right? And so you try to follow the changing world model like that.
Perfect. Thanks very much, Kuba. Yeah, it's a great question, this issue of data drift. Now, I've got a question myself. By the way, I really dislike this conversation that, data is the new black gold or is like oil. But I do agree with you. It has value when you do something with it. Otherwise, it's just horrible, black, smelly, and polluting. So this is my question. Is more data always better? Because I think a lot of people think that if they just feed in more data elements into an artificial neural network model, it's going to give a better result. And I can tell you what's at the back of my mind is that if you deal with a big enough and complex enough data set, you will often find spurious correlations. So it looks like there's a correlation, but actually it isn't. There's some other factor that may be correlated, if any at all.
That's it. Yes.
Is more data always better? Is it the case we just keep throwing data at it until it comes up with the right answer?
So, of course, in the effort to kind of boil down predictions for people, I think this came up, right? Oh, more data, always better. I think the kind of notion that people want to convey in that more data equals better is that the more data you have, the more kind of possibility that there is good data in it there is, right? But I agree with what you, I think, saying between the lines, that nothing's for free, right? There's no such thing as free lunch. You have more data, you still need to look at it, right? You still need to find what's the valuable part of the data, right? You might have 500 columns in this data set, but only 3 are actually they have a higher predictivity, right? Like they predict the output better. And so it's not going to happen automatically. It's not that you will have more data, things will be better, right? You still need a human kind of to look at the results, at the analysis of the data, and how to feed it into the machine learning algorithms. But I think that's the notion here. The more data you have, the more probability that there is good data in it. That's the outcome I take out of this, and I'm always happy to get more data than less data, because I can then choose rather than having to, for example, artificially expand the data set, right? Because that's how sometimes this is done, right? You get a little bit of data, and you actually create artificial data that looks similarly to the small real world data set that you get. But just because the way the training works in some of the machine learning architectures, you need more data that, for example, is artificially created.
Lovely. Well, look, thank you very much, Kuba. Great presentation. Really enjoyed it. I've, as always, taken lots of notes here. We could talk for ages, but unfortunately, we're out of time. So thanks once again. And I look forward to talking with you again personally really soon. But until then,
All right. Thank you, Peter.
bye-bye.
Bye bye.